Hey everyone, welcome back. Today I want to talk about limits from a different perspective. In the last video, our primary concern was in finding limit values from graphs. In this video, on the other hand, we're going to look at limits from the perspective of what they can tell us about graphs. So the primary concern of this video isn't to find limits from graphs, but to use them to tell us things about graphs. Specifically, we're going to use them to discuss whether graphs are continuous. Now here I'm carving out 4 pieces of 4 different graphs, and I want you to ask yourself, which of these 4 pieces are continuous at x equals 3, and which ones are discontinuous at x equals 3? No worries, just fall back on your common everyday non-mathematical understanding of what the word continuous means, and answer that question. In fact, go ahead and pause the video and take a handful of seconds to label these 4 either continuous or discontinuous. Okay, so labeling left to right, the first one is continuous at x equals 3, whereas all the rest are discontinuous. The second graph has a hole, the third has a sudden vertical jump, and the fourth has a vertical asymptote that breaks the graph at x equals 3. These are all types of discontinuities. Now a very nice way to get a handle on continuity versus discontinuity is to ask yourself, can I have drawn this picture without lifting my pencil up at all? Of course, we don't need to lift our pencil to draw the first graph, but to draw the second, third, and fourth, as you can see here, we would need to lift our pencils. So they are not continuous at the x-coordinate x equals 3. Now it is high time to bring limits into the picture. I want us to fill out this information here. What are the 4 function values that I've written left to right? What are the 4 left limit values? And what are the 4 right limit values? So finishing off the left limit values and then writing the right ones. What are these 12 values? Now then, for this first trio, the function value is 5, the left limit value is 5, and the right limit value is 5. For the second trio, even though the left limit and the right limit both equal 5 again, this time around the function value is 7, and that's why it's discontinuous. And because of that difference, we had a hole. For the third batch, f of 3 is 7, and the right limit is 7, but the left limit is 5. That's why we had a vertical jump. They didn't match. And finally, for the fourth graph, oh, this is just all sorts of a mess. F of 3 doesn't exist. The left limit is positive infinity, so it doesn't exist. And the right limit is negative infinity, so it also doesn't exist. This one didn't do anything right, which is why it gets all red marks. Now then, the takeaway regarding how limits relate to continuity should be clear. It's only when left limit equals right limit equals function value for a certain x-coordinate that the graph is continuous at that x-coordinate. If that is violated in any way, we'll have a hole, or we'll have a jump, or we'll have a vertical asymptote, and the graph will not be continuous at that x-coordinate. Left limit equals right limit equals function value. That's the criteria for continuity. So in light of this, let's hammer that out more formally. Here is the definition of local continuity. Local continuity. We'll start with the informal definition. Informally, what we have here is that to be locally continuous at a certain point, 3 things need to happen. The left and right limits need to exist. They have to be a finite number. They have to equal each other. So this is not too different from the last video, but the new condition that adds on to the last video is that they have to be equal to the function value at that point. So 3 things: exist, equal each other, and equal the function value. More formally, way of saying the same thing, is that a function is locally continuous at some arbitrary point c, comma, f of c, if and only if the function value exists and the left limit equals the right limit equals the function value. And it's that second thing right there that I'm boxing. This is what you really, really need to know very well. Left limit equals right limit equals function value That's the core definition of continuity. If that happens, the graph is guaranteed to be continuous at that spot. Also, y'all, the left limit equaling the right limit, this is what I'm showing here in red, also permits us to condense and write the definition of continuity in terms of the overall limit. That stuff in red is the overall limit, and if that overall limit equals the function value, it will be continuous. This brings us to 3 unique ways a function can be discontinuous at a spot. And we'll set this guy up in a cloud. Nice white cloud. First way a graph can be discontinuous at a point is that the limit value, the overall limit value, doesn't exist. Secondly, the function value doesn't exist. That's another way it could be discontinuous. And third, maybe both the limit value and the function value exist, but they happen not to equal each other. So 3 ways of being discontinuous. Let's illustrate these in the context of the pictures above. Let's start with that second picture. The reason that second picture was discontinuous is that it violated condition number 3. Overall limit existed and equaled, 5, but the function value was 7. They didn't match. The reason why the third picture is discontinuous is because it violated condition number 1. It satisfied condition number 1. The overall limit didn't exist. And the third one, it violated 1 and 2. The overall limit didn't exist, and neither did the function value. It was just all around a discontinuous sort of chap. Speaking of discontinuities, we should put some more formal titles on the table besides holes and jumps and asymptotes. So, since 3 seems to be the magic number, let's give formal names to these 3 types of discontinuities. Also set this guy up in a cloud. Formally. First, holes are more formally called removable discontinuities. By the way, you're going to want to know these formal titles. They pop up all the time on quizzes, tests, AP tests. Holes are removable discontinuities more formally. Vertical jumps are more formally known as jump discontinuities. And thirdly, vertical asymptotes are, unsurprisingly, called infinite discontinuities. Those are my 3 types of discontinuities. And I must say, I really like the way this page turned out. It's like Willy Wonka was a mathematician. Willy Wonka and the Mathematical Factory. Now, before we work out a couple of examples, it is natural to wonder, what on earth does locally continuous mean? To illustrate, let's pick a graph that we know from foundations is not continuous everywhere. How about 1 over x? That chap looks like so. Clearly, it is not continuous everywhere. At x equals 0, it breaks. However, setting aside x equals 0, this graph actually is locally continuous everywhere else. To see what I mean, let's pick x equals 1/2, x equals 0.5. Left limit equals right limit equals function value right there. And this is true at any x-coordinate on the graph that isn't 0. Down here, for example, left limit equals right limit equals function value. Again, another point down there, left limit equals right limit equals function value. A point up there, left limit equals right limit equals function value. That's going to hold true for every single x-coordinate on the graph that isn't 0. So the function is locally continuous at all these points. Now, what locally continuous means in a more abstract sense, which is what I'm drawing here in blue, is that there is guaranteed to exist some interval around that point on which the graph is continuous. It's unbroken. You can trace it without lifting up your pencil, i.e. left limit equals right limit equals function value. The only point where you can't pick an interval of continuity is at 0. Because then you have to pick an interval down there, where the graph is pointing towards negative infinity, and the other one would have to be up there at positive infinity. Okay, so I am sketching a graph here in a gloriously speedy fashion, I might add. And after I finish, I want us to pause the video and to do the following prompt. It's a prompt that comes up a lot on quizzes, tests, AP exams. Very worthwhile to know. Just throwing that out there. But I suppose for now I should finish my aesthetically pleasing drawing 3 or 4 dashes. With those in mind, I want us to label and formally classify all discontinuities. So go ahead and pause the video and give that a go. Okay, so back at it, just working left to right. At x equals -5, there's a discontinuity. What type is it? It is a jump discontinuity because the overall limit doesn't exist. At x equals 2, f has a removable discontinuity because the function doesn't exist. The overall limit exists, but the function value doesn't exist. At x equals 4, f has a jump discontinuity. Again, the overall limit doesn't exist. Left limit does not equal right limit. Finally, at x equals 5, there's an infinite discontinuity. Neither the overall limit nor the function value exist. Neither exists. This final example here, and I'm not going to lie, it is a bit of a weird one. We want to find the value of capital A that renders the following function continuous. And this function is a piecewise fellow with a quadratic up top, ax squared minus 3x plus 4. That happens whenever x is greater than or equal to 2, and a line ax plus 8 whenever x is less than 2. Again, I want to find the capital A, the value of capital A that makes this guy continuous at x equals 2. Again, no matter how weird it looks, fall back on your definition of continuity. Left limit equals right limit equals function value. This is what we want to be true for an x-coordinate of 2, for it to be continuous there. I just realized I'm using watermelon, a watermelon scheme. Oh well, could be fun. Let's go with that. Definition of continuity. Let's start with the low-hanging fruit. The function value is the easiest thing. For f of 2, I'm just going to stick it in the top piece because it's a top piece that applies when x is equal to 2. Greater than or equal to 2, so I plug it into the top piece. Doing a bit of algebra gives you 4a minus 2 for f of 2. Likewise, for the right limit, we are approaching 2 from the right. So we're approaching it by going through values like 2.1, 2.01, 2.001, 2.001. So I'm dealing with that top piece, that quadratic, the parabola, which lets us rewrite the limit like so. And the benefit of rewriting like that is that we can pretend we are dealing with an entire parabola. And for parabolas, for any point you pick on them, the right limit value will always equal the function value. So that's what I'm writing here. Right limit value always equals the function value anywhere on a parabola. Parabola is nice and continuous. So this guy, up top here, that I've starred in purple, must equal that, a times 2 squared minus 6 plus 4, which is also 4a minus 2. On the other hand, for the left limit, which is the final limit we have to deal with, we are approaching 2 from the left. So we're going through x values like 1.9, 1.99, 1.99999. And so, for this approach, we're dealing not with the top piece, but with the bottom piece, the line ax plus 8. And the benefit of writing it like that is that we can pretend we are dealing with an entire line. And lines, just like parabolas, for any point you pick on them, the left limit value will always equal the function value. It's continuous. It's continuous everywhere. So, starring that, I can say it's equal to the function value of the line, which is a times 2 plus 8, or 2a plus 8. And penultimately, we want these left sides to be equal for continuity. But the left sides are the right sides. So saying that we want left limit equals right limit equals function value ends up being the same thing as saying we want 4a minus 2 to equal 4a minus 2 to equal 2a plus 8. The 4a minus 2s are redundant, so we just say 4a minus 2 equals 2a plus 8, plus 2 both sides, minus 2a both sides, and we get a nice a equals 5. Boom, mic drop, done. Bit of a doozy, admittedly, but definitely a good question to know for assessments. For tests, quizzes, AP exams. Definitely know how to do these kinds of questions. Peace.